Last time I went over the stationary phase approximation, and basically it's an exercise in mathematics. It's an approximation for an integral in which you've got a rapidly oscillating integrand. Here we're thinking of kappa as being small, which is what makes an integrand oscillate rapidly. And I think it went over all right in the one-dimensional case, but for the multi-dimensional case I was pretty sketchy. So I want to start today by filling in more of the details about this multi-dimensional result here, the stationary phase approximation. The variable x here is shorthand for x1 to xn, so it's in dimensions, as you can see. And the basic idea of the approximation is that the integral integrand is dominated by the regions of the variable integration x, region of x space, around which the phase phi is stationary. Stationary phase point is defined as simply one where the gradient of phi is equal to 0, and we call that x bar. And so the basic idea is to just expand the exponent around the stationary phase points, carry it out the second order, and then do a Gaussian integral. To do it in somewhat more detail, let me write it like this. So let's take let's take a point x, and let's write it as a stationary phase point plus a correction I'll call y, like this. Then we'll expand the phase phi of x in powers of y, which we think of as small. So it becomes phi of x bar, the stationary phase point, plus first correction is the sum on I of y sub I, the derivative of phi with respect to xi, evaluated at x bar. And then the second correction, just doing a Taylor series, it's a multi-dimensional Taylor series. We have sum on I, j of yi times yj times the second derivative of phi, xi, xj, evaluated at x bar. And then there's cubic and so on terms out here, which I don't bother to write down. So this is the expansion of the phase in the neighborhood of the stationary phase point. Now the first order term vanishes because that's the definition of the stationary phase point, is where the gradient of phi is 0. And this is why I went on to the second term, because it's the first non-vanishing term after the value of phi on the stationary phase point itself. So I want to take this phi of x and plug it in here into this exponent. You see the first term is just going to be a constant, and the second term is going to give us a Gaussian integral. If I call this integral I, just to give it a name here, the result is going to be that I is equal to an integral dnx. And then for the phi of x bar, I'm just going to get e to the I phi of x bar over kappa. And then there's a correction from second order. To make this a little easier to write, allow me to take this matrix, the second derivative matrix of the phase, evaluate the stationary phase point, and just define it to be Mij. M just stands for matrix. That's just save writing. And likewise, let me take the entire second order expression here and write it this way as y transpose times m times y, where y is being viewed as an n-dimensional vector, which is being sandwiched around the matrix M. That's just what this whole expression means. So if I do this, and there's another term here in this integral, it's e to the I over 2 kappa, and then we've got y transpose times m times y. And this is now an approximation because we truncated the expansion of the exponent in second order. But you can see that as far as the first factor is concerned, the phi evaluated at the stationary phase point is just a constant. It can be taken out of the integral. And as far as the rest of it is concerned, it's a Gaussian integral. It's in multi-dimensions now in the matrix M. And it's a purely imaginary exponent, but it's basically a Gaussian integral. The variable of integration dnx is the same thing as dny, because x and y just differ by a shift, just a change of origin is all it is. And this thing then turns into the central integral is the integral over y times this Gaussian exponent. Now, to proceed with analyzing this, let's let y be equal to r times z, where y is an old vector of coordinates and z is a new one, and r here is an orthogonal matrix. And if we make this substitution in the exponent here, then the exponent, which is y transpose times our matrix m times y, becomes equal to z transpose times r transpose times m times r times z. It becomes a new coordinate z transpose z sandwiched around a new matrix, which is r transpose mr. Now, M is a symmetric matrix. It's a real symmetric matrix because it's just the second derivatives here. So we can choose this R matrix, orthogonal matrix R, to diagonalize this. And let's do that. Let's call this lambda, which is diagonal. And then lambda, you see, contains the eigenvalues of the original matrix M. Also, let's note something else, which is that the Jacobian, or that the volume element dny is the same thing as dnz, because the orthogonal matrix here, which occurs in the coordinate transformation, has a determinant which is 1. And so the remaining integral here, if I have space to write it down, is first of all this constant factor. It's e to the I phi of x bar over kappa. And then the remaining integral is integral dnz. And then we get e to the I over 2 kappa in the exponent here. And then this quadratic form now turns into this. We can write it this way. It's the sum on j of the eigenvalues, called them lambda j, times c sub j squared. And now the point of this is that this resulting integral in z now factorizes into a bunch of one-dimensional Gaussian integrals, and in effect reduces this to this multi-dimensional case down to the one-dimensional case. Now, I'm sort of short on the room here because I got so much on the board. But let's just look at this integral here. And let me do it up here on this board up above. I'm trying to cover it all up. So the remaining integral here turns into a product of these one-dimensional integrals. So our I is equal to this prefactor, e to the I phi of x bar over kappa. That's the phase evaluated at the stationary phase point. And then the remaining integral is the product of one-dimensional integrals, so all that is the product over j. And these one-dimensional integrals, as I said, I derived the one-dimensional stationary phase approximation last time. Each one of those is going to turn into this. It's going to be e to the I pi over 4 times the sine of the eigenvalue, lambda j. And then what you get is the square root of 2 pi kappa divided by the absolute value of lambda j. That's the result of doing this integral. Now, when we take the product over j over all the variables of the lambda j's down here in the denominator, that's the product of the eigenvalues. That's of course the same as the determinant of the matrix. So the product of the lambda j's is the determinant of this matrix M, which is the same thing as the determinant of the second derivative matrix here, the evaluated stationary phase point. And that explains this determinant under the square root that you see down here in this answer that I'm quoting. That's where that comes from. As far as the product of the 2 pi kappa, since there's n of these, as opposed to 1 at the end, this is going to give you 2 pi kappa to the n. And that explains this factor here under the square root, right there. And as far as the product of the signs of the eigenvalues are either positive or negative. We will assume this matrix is non-singular. And so the product of the signs times e to the I pi over 4 is just equal to e to the I pi over 4 times the number of positive eigenvalues minus the number of negative eigenvalues. And that's exactly what this factor here is, e to the I nu pi over 4, where nu is defined as nu plus minus nu minus, and nu plus and minus the number of positive and negative eigenvalues of the second derivative matrix. So that's the derivation of the stationary phase approximation for multidimensional integrals, and I'll try to put a separate box around that. That's the main result. Now then, last time I was in the process of applying this to the path integral. The general idea here is that this is a discretized version of the path integral. The sum which occurs in the exponent is a discretized version of an action integral as it occurs in classical mechanics, an integral of Lagrangian along a path. And so this suggests that the path integral is connected with the Lagrangian formulation of classical mechanics. In fact, we know according to Hamilton's principle that the paths that cause the action to be stationary are the classically allowed orbits. And so this suggests that the path integral is connected in a semi-classical way to Hamilton's principle in classical mechanics. So if we think about h bar being small, in order to study the semi-classical limit of the propagator, it suggests that the h bar here should be identified with kappa in this mathematical formula. That's the small parameter. And the integrand is a rapidly oscillating integrand. See, it's a purely phase factor in this integrand. It's a rapidly oscillating integrand when h bar is small. So the first thing we do in trying to fit the path integral to this general formula is, as you see at the top of the board, we'll just replace kappa by h bar. And then as far as the phase function is concerned, it appears here, that's everything else in this exponent except for the h bar. So it's epsilon times that sum. That's the phi that you see up there. That's, in fact, the discretized approximation of the action integral. In other words, as n goes to infinity, this turns into the action integral along the path. All right? All right. And then for reference here, I've taken derivatives of phi with respect to the x's. Oh, here's another thing to note, too, is that in this mathematical formula, I said x goes from 1 to lowercase n, but in the path integral, the x's go from 1 to capital N minus 1. Remember that x0 and x capital N, which is the same as x, are just fixed parameters of the propagator, and they're not variables of integration. We only integrate over intermediate points. That's the 1 to n minus 1. So another thing that I might put up here is that as we're going to also take n goes into n minus 1 and trying to convert this mathematical formula into the application to the path integral. All right. So anyway, then here's the derivatives, which I've just worked out by taking derivatives of that phase function, which occurs in the discretized version of the path integral. Now, in applying the stationary phase approximation, the steps involved are basically these. The first thing is you need to find stationary phase points, the x bars that are indicated here. And those are the roots of the gradient of the phase function equals 0, the places where the phase function is stationary. That's why they're called stationary phase points. So in the application to the path integral, what we need to do is take these first derivatives here, which are written out here in general form, and set them equal to 0. So if we take partial phi with respect to xi and set it equal to 0, and I showed this last time, this means the thing in the square brackets goes to 0. This is actually a discretized version of Newton's laws. In other words, it turns into this. It turns into m times xi plus 1 minus twice xi plus xi minus 1 over epsilon squared, which is a discretized version of the acceleration, is equal to minus v prime of xi, which is the force. And so in the limit in which n goes to infinity, this turns into a differential equation, which we can write this way: d squared x of tau d tau squared is equal to minus d prime of x of tau. And this is just Newton's laws for the path x of tau. So it's the classical paths in the limit that it goes to infinity. It's the classical paths of the stationary phase points. They're points because they're points of path space. And to follow this notation down here where I was using a bar on the stationary phase point, perhaps I should do that also here. Put a bar on this to distinguish the paths which are the solutions of Newton's equations, classically allowed paths, from any old path which can be put into the action functional above. All right. In any case, this is just a repetition of the usual derivation that the stationary action leads to the classical orbits. It's usually done in classical mechanics courses. All right. So then we determined the stationary phase points. That is to say, paths. They are the classical paths. All right. So that's the first step, and that already allows us to speak of this exponent, which occurs here in this stationary phase approximation. What does it mean the exponent is? It's the phase evaluated on the classical paths. So let's go here and let's write down some stuff. We're going to have our propagator, here, x0 and t, is going to equal to a whole lot of stuff that has to do with all of these prefactors here, which I'll get back to in a minute. But just to look at the final phase here, it's going to be a bunch of stuff on this space for it, and then it's going to be e to the I over h bar times the phase function evaluated on the classical path, which is what we're calling x bar. Well, that's the same thing as a of x bar of tau. But the phase function evaluated on the classical path is also what's called Hamilton's principal function. This is the definition of Hamilton's principal function. For simplicity, let's assume there's only one classical path connecting the endpoints at n times. In that case, Hamilton's principal function depends on the endpoints at n times as I've indicated here. It's usually called S. But it's just the integral of the Lagrangian now along the classical path, not some crazy path that's not visible. And then, as I mentioned last time, Hamilton has shown that this function satisfies certain differential equations. If you differentiate with respect to the parameters, the x, x0, and t, that S depends on, you get the final momentum with differential with respect to x, the initial momentum with differential with respect to x0, and minus the energy or Hamiltonian as a differential with respect to time. I didn't prove these, but these are well-known results, and these are called generating function relations, which are well-known in classical mechanics. In any case, the result of this is that the phase of the propagator can now be written this way as e to the I over h bar times s of x0 and t. It is the classical Hamilton's principal function appearing up there in phase. And now what we need to worry about is the rest of this stuff, which is connected with all of these prefactors here, and phases too. There's a constant, there's a real prefactor, and then there's a phase. Now, there's a lot of trees here in this forest, so I don't want you to lose sight of the forest before I get into all the trees. The basic intuitive idea of this is that, as I say, is that the integral is dominated by the regions of x space that surround the stationary phase points. So if x space is going to be a path space, then it means the integral in the path integral is dominated by the regions of path space that surround the classical paths. You might say it's classical paths plus small fluctuations around them. That's the language that's commonly used for this. How far do you have to move away from the classical paths? The idea is you move far enough away that there's enough dephasing in the oscillations of the integrand to start killing things off because they become just plus and minus signs that cancel each other out. There's some central lobe or some central region around the stationary phase point in which the integrand is in phase, has the same phase as it does at the stationary phase point. And that's where the contributions to this integral is coming from. So what all these prefactors do is they tell you how far you can move away, in this case from the stationary phase point. When we do apply to the path integral, it's going to be how far away you can move from the classical path and still have the action functional be approximately in phase with the value it had on the classical path. In other words, this takes into account fluctuations. This is going to take into account fluctuations around the classical path. Well, all right, so that's the intuitive idea, and now I'll get into the details, more of the details of this. It's clear that in order to look at this, to examine this, we're going to need the second derivatives of phi. And I've evaluated them here. It's just writing this out of this form here of log. This is just taking the derivatives coming down. Taking these second derivatives. The way I've written it is m over epsilon times something in the square brackets here. To give this thing in the square brackets a name, let me, since I have a little room here, let me kind of do it like this. Let me call this here just Qij, just to give it a name. This is the matrix Q. In effect, the second derivatives of phi are equal to a constant m over epsilon times Qij. Now, we'll worry about Qij in a minute, but right now let me concentrate on m over epsilon. So sorry to keep bringing this up and down. I wish I had more boards here. But in between the k and this phase factor, there's going to be prefactors here. And this is what I want to work on right now, is the prefactors. So let's take a look at what those prefactors are. In the first place, there is this normalization constant here, which comes from the discretized version of the path integral. This has an imaginary unit downstairs. Square root of I is interpreted as e to the I pi over 4. This is square root of I to the minus n power. So let me take care of the prefactor first. Take care of that prefactor first. So the prefactors are going to be equal to e to the minus I n pi over 4, which takes care of that phase. And then I'll copy everything else except the I, m over 2 pi epsilon h bar, to the n over 2. And that takes care of, that's just another way of rewriting this prefactor right here. But in addition, by doing the stationary phase approximation, we're going to get another phase here, nu, the I nu pi over 4. The nu is going to be the difference between the positive and negative number of positive and negative eigenvalues of this second derivative matrix times this whole square root. So notice that this has got the derivative of v squared phi, but the v squared phi is m over epsilon times the semicolon q. So, and the kappa here is the same as HR, so I've covered it up, unfortunately. This is going to turn into this. It will be the square root of 2 pi h bar to the n minus 1 power. And then it's going to be determinative of this thing, the second derivatives, but this is an n minus 1 by n minus 1 dimensional matrix. So we get the factor of m over epsilon to the n minus 1 power. And then what's left over is the determinant of q, which I have to put absolute value signs on. So those are the three factors. All right. The prefactor that came from the path integral itself is right here. And you can see it diverges rather badly when n gets large, because it's got an epsilon in the denominator. The epsilon, like the delta t, is t over n. So it goes to 0 in the denominator, and the exponent is getting big. This goes to infinity like n over n. It's a really, really bad divergence. But it has to be compensated, will be compensated by the rest of the integral, as you'll see. In fact, if you look over here at these factors that came from the stationary phase approximation, I've got a 2 pi h bar divided by m over epsilon. It's really the same thing as in these round parentheses here. The power isn't quite the same. This is n minus 1 over 2 because of the square root. But anyway, it combines with that just to leave behind just a single 1/2 power. And so this turns into this. Oh, and I also forgot to either the I nu pi over 4 that's supposed to be in the stationary phase approximation. So these prefactors now turn into e to the I n minus nu times pi over 4. That's the phase of the thing coming from here and here. And then the m's and 2 pi epsilon h bars, if I take care of that and this, I just get m over 2 pi epsilon h bar, now to just the 1/2, single 1/2 power. Most of the divergence is gone now, you see. And then I got 1 over the square root of the absolute value of the determinant of q. Okay, so this is what's left of the prefactors. It's starting to simplify some. Now, as far as the determinant of q is concerned, here's q. It's this thing in the square brackets here. This is a n minus 1 by n minus 1 dimensional matrix, and in the limit that n goes to infinity, it's going to turn into an infinite dimensional matrix. And so we have to find the determinant of an infinite dimensional matrix. Sounds like a tall order, and in fact, often in dealing with path integrals, it's these matrices, or these, in effect, volume factors in path space are the most difficult parts. I used to give a homework problem on how to evaluate this thing, but I think it's too hard, so I will inflict it on you. And I think what I'll do instead is just try to outline, in general terms, how one derives this thing and how one can evaluate this ultimately in simple terms. So again, I hope you don't lose sight of the forest for the trees, because the real meaning of all of this is just in effect giving you an indication of how far you can move away from the classical paths in path space before you dephase the path integral. So, allow me now to work on this determinant of q. The first thing to notice is that the answers ought to be finite as capital N goes to infinity, and there's still a remaining epsilon in here. So we must expect that in the limit that N goes to infinity, is that determinant of q must go as 1 over epsilon. It's going to have to do that to cancel this epsilon there. And in fact, I'll show that this is actually true. It's also true that as n goes to infinity, you'll find that nu minus n approaches a nice finite value, which it has to if you're going to get a definite phase for the answer. All right. So let's just take this matrix Q then and try to write it out. So this is Qij. Here it is. It's the thing in the square brackets in the middle of the board up above. Let's look at the first three terms. These are Kronecker deltas here. The first term is just 2's on the diagonal. And these terms here with minus signs are minus 1's on the upper and lower off diagonal elements. So if I just take those first two terms, the right Q here is a big matrix. It is indeed big. It's going to have 2's on the diagonal coming down like this, going all the way down, and the last one will have a 2 here. And then it's got -1's on the off diagonal, on both upper and lower off diagonal. Down here, there's no off diagonal there because that's at the end, but there's an off diagonal on this side, -1, going down to -1 there. So this is actually a tri-diagonal matrix, and it's got zeros everywhere else. That helps a lot in finding its determinant. This tri-diagonal matrix that I've written down so far, if that's all there was to it, would be a discretized version of the second derivative operator. In fact, that's what it turns into in the limit. It gives us our acceleration. In any case, there's an additional correction here coming from the potential. And in order to avoid safe writing, let me call Ck is equal to epsilon squared over m times v double prime evaluated in xk. And so I need to, this is times the diagonal elements, delta ij, so I need to subtract Ck from the diagonal elements. And so I get 2 minus C1 here, 2 minus C2 there, 2 minus C2 there, going all the way down to 2 minus Cn minus 1. All right. So how do we find the determinant of that thing? Actually, to find the determinant of it in the finite form would actually be kind of hard, but in the limit n goes to infinity, it's actually simple. So it works like this. Let's take a k by k block of this thing. Let's call this a k by k block. Let's call dk to be equal to the determinant of the first k by k block. And remember, I'm just going to outline how one does this, and not go into total details. If you use Cramer's rule on this dk matrix, which is pretty easy to do because you've got rows and columns that have a lot of zeros in them, you see. It's pretty easy to derive a recursion relation for the dk's. And it ends up looking like this. It is mass m times dk plus 1 minus twice dk plus dk minus 1 divided by epsilon squared equals minus v double prime evaluated at xk plus 1 times dk. And you can derive this for yourself in a few minutes. It's easy to do. But you see, on the left-hand side, again, there's a discretized version of an acceleration. And on the right-hand side, you've got the potential evaluation. This x I should really make an x bar because we're only interested in evaluating this on the classical path. The stationary phase points, in other words. So this is x bar is assumed to be a known function of k in the discrete case. In the continuous case, it becomes a discrete definite function of tau, where tau is this continuous variable that goes between the initial time 0 and the final time t. In any case, this turns into, in the limit that n goes to infinity, into a differential equation. But before I do that, allow me to take into account the fact that determinant q is going to go as 1 over epsilon. We expect that. So let's just do a simple change of notation. Let's let dk equal to 1 over epsilon times fk. Just to get another name for something, fk. And to scale out the epsilon, that's all. And if we do this and we get the same equation, of course, it's a linear equation in D, so it becomes the same equation in f. Fk plus 1 minus twice fk plus fk minus 1 divided by epsilon squared is equal to minus v double prime of x bar k plus 1 times fk. It's the same thing, same equation. And then in the limit that n goes to infinity, this turns into m times v squared f, which is now a function of continuous variable tau, d tau squared, is equal to minus v double prime evaluated at x bar of tau, that's the classical ordinate, times f of tau. Leave into that in the limit. It becomes a differential equation. And one that actually has an interesting interpretation in classical mechanics regarding nearby orbits, as I'll explain in just a moment. But before I do that, let me add that one can also work out what the boundary conditions on f are. You have that f at 0 is equal to 0, and you have f prime at 0, or let's call it f dot, because it's a time derivative, of 0 is equal to 1. Those are the conditions that come out. You get these conditions by just looking at the first couple of blocks. The first block when epsilon goes to 0, and the determinant of the first two when epsilon goes to 0. You can take the limit and get the derivative. All right. So this is a definite differential equation with definite boundary conditions, and so there's a definite solution. And the f of t then is going to be interpreted as epsilon times the determinant of this q in the limit that n goes to infinity. All right. Now, let's examine this equation here. It turns out this equation is closely related to the problem of nearby orbits in classical mechanics. Here's a place where such a problem arises. You send a spacecraft to Mars, you fire rockets, and the spacecraft is launched onto a ballistic trajectory after it gets out into space, and the rocket engines are turned off. So you make measurements of the trajectory, and you find that it's not actually right because there was some bad weather and passing through the atmosphere, and so you need to make some corrections to the trajectory. This is typical, as a matter of fact. So you've got a trajectory. Let's say I'll draw the trajectory in phase space. Let's say there's an x0 and p0 initial point, and then there's a trajectory that ends up at a final point, x of t and p of t at some final time, like this. There's some elapsed time t involved here. Let's say this is t equals 0. And unfortunately, so this is your spacecraft after it's been launched, and you find that the final position is not what you want. You need a different final position. So this gives rise to the following problem in classical mechanics. Suppose I make a small perturbation in the initial conditions, call it delta x0, delta p0, like this. This will give rise to a perturbed orbit, which will be nearby the original orbit. And at the final time, it will give perturbations in the final position, delta x of t and delta p of t. And now what we'd like to do is, for the Mars problem, is we know what delta x of t is because we want to correct for the error. And we'd like to find out what perturbation and initial conditions do we need to impose in order to get the right delta x of t. Well, in general terms, solving differential equations here gives us the final condition x as a function of the initial conditions, the initial position and momentum and the time. And likewise, the final momentum is also a function of the initial position, the initial momentum, and the time. This is just a general solution to the equations of motion. And so just by differentiating this and using the chain rule, what you get is that delta x and delta p, the deviations in the orbit at the final time, is the derivatives of the final position with respect to the initial position, the final position with respect to initial momentum, final momentum with respect to initial position, and the final momentum with respect to initial momentum. There's a 2x2 matrix like this, and then this multiplies delta x0, delta p0. This is just using a chain rule to get the small perturbation in the final conditions as a function of the small perturbation in the initial conditions. All right, so to solve this problem, one needs to know this matrix. All right, now, I am running out of space. So, let's see if I can do it here in the space which is left. Let's go back to this equation. The x bar here at t was our classical orbit. And so it satisfies m times d squared x bar of t d tau squared is equal to minus d prime of x bar, d prime of x bar, d x bar of tau, d prime of x bar of tau. This is just Newton's laws for the classical orbit. Now let's consider a nearby classical orbit. Let's take x bar and replace it by x bar plus delta x. We're interested here in an orbit which is still a classical orbit. It's still supposed to satisfy the equations of motion, but it's close to the original classical orbit. So if I plug this in here and linearize this equation, carrying out a first order in delta x, what we get is m times d squared d tau squared of delta x of tau is equal to, on the right-hand side, I plug this in, expand it out to first order, it's going to be minus d double prime of x bar of tau times delta x of tau. So this is the equation for the deviations in x, the x deviations. Now notice it's exactly the same equation as the differential equation for the determinant of this matrix. These given initial conditions. And so, what is the solution? The solution is given by a matrix like that, matrix equation like that in terms of initial conditions. So the idea is that if I want to take delta x0 equal to 0, and delta x0, we're going to set that equal to 0. As far as delta p0, this is the same thing as the mass times delta x0 dot. But I want to identify the f here with the delta x because it's the same equation. So f0 dot is 1, so the delta p0 is going to be just m. And so the result of this is that f at the final time, and the mass times f dot at the final time, which is like the final momentum, is equal to this same matrix, dx dx0, dx dp0, dp dx0, and dp dp0, applied to 0 and m, like that. And all we're really interested in is this f of t part. And so this says that f of t is equal to, it's this component of this matrix here, partial of x with respect to p0 times the mass m. And that's our solution that we want for this differential equation satisfying those boundary conditions. It's directly related to the derivative of the final position with respect to the initial momentum multiplied times the mass. All right. Now, so I'm going to erase this now because I don't need this anymore. Try to finish it up here. So the f of t, which is the final f, to copy it again, is equal to this. Partial of x with respect to p0. Now, the partial of x with respect to p0 is a derivative of the final conditions with respect. I'm looking for an equation I wrote. I wrote it right here. It's a derivative of the final x with respect to the initial momentum, but it holds the time and the initial x0 fixed. So to be explicit about that, let me put the x0 here. It holds x0 fixed. Now allow me to transform this. It turns out this can be written in terms of Hamilton's principal function. It works like this, is that this is the mass. We write it this way. It's partial of p0 with respect to x. I'll just turn the derivative upside down at constant x0 and put an inverse on it. That's okay. Now, again, I need three boards here at the same time, which I don't have. But here's Hamilton's principal function. It's a function of the initial position, the final position, and the time. And here's Hamilton's generating function relations. In particular, ds dx0 is equal to minus p0. And s is a function of x0 of t. And the result is that this is the board I need, I think. The result is that this can also be written as, to the minus sign, m times the second derivative of s with respect to x0 and x, to the inverse minus 1 power. And this implies that gosh, now what have I done here? I've probably erased what I need. The d, t was going to be 1 over epsilon times f. And so the absolute value of d of t, which is that determinant that's needed in the matrix, is m over epsilon times the absolute value of b squared s dx0 dx1 or dx to the minus 1 power. And this is the same thing as this determinant of q, and the limit then goes to infinity. It's the determinant of q, which, where was I talking about prefactors? It's right there. And so you see nicely the m over epsilon that appears there cancels out the m over epsilon over there, so the result is finite. And the derivative of this infinite dimensional matrix turns into just a second derivative of Hamilton's principal function. All right, so let me bring this down. And now I no longer need this over here, so let me erase this. And so dealing with the prefactors, this thing turns into, I'll get the phases in a minute. But as far as these square roots are concerned, what's left is just the, it's just 1 over. It's 1 over the square root of 2 pi h bar. And then this determinant q now turns into the second derivative of Hamilton's principal function with respect to initial and final positions to the 1/2 power. There was a minus 1, but this is in the denominator. It got turned into the numerator, and there's the square root still there. The phases are this part here. These can be analyzed this way. Mu is equal to mu plus minus mu minus. It's the number of positive minus negative eigenvalues of this matrix Q, which is going to, in the limit, is turning into an infinite dimensional matrix. So one of these numbers, mu plus or mu minus, has to be infinite. It's going to approach infinity. On the other hand, n here, on the other hand, the sum of the positive and negative eigenvalues is the total number of eigenvalues in the matrix, which is equal to n minus 1. So I want nu minus n, so let me subtract that from that, and I get nu minus n plus 1 is equal to, the nu pluses cancel. You get minus twice nu minus, or if you allow me to use my fingers and bring that 1 over here, nu minus n is minus twice nu minus minus 1. For the minus 1, that gives me an e to the I pi over 4. Let me bring that down into the denominator here. Actually, put some I down there. I gets inserted there if I do that. And then for the nu minus, let me do this. Let's give another name for this. Let's like leave the same thing as nu minus. It's easier to write. This is the number of negative eigenvalues. And this is multiplied times 2. The 2 times pi over 4 gives a pi over 2. Okay. So I don't expect you to follow all these details. If you had extra time to study, which you don't, you could easily follow this. But I just want to give you most of the outline of how this is all derived. In any case, the result is the following. It is that the propagator, k of x, x0, and t, in the stationary phase approximation, is equal to e to the minus I mu pi over 2, divided by the square root of 2 pi I h bar. It is the absolute value of the second derivative of Hamilton's principal function with respect to initial and final conditions to the 1/2 power. And then it's e to the I over h bar times Hamilton's principal function x, x0, and t. And this is the stationary phase approximation to the propagator. It provides the principal link between classical mechanics and the time evolution in quantum mechanics. All right. Now, about this mu, what is this mu? The mu is the number of negative eigenvalues of that matrix Q, which was going to infinity, becoming an infinite dimensional matrix. In the limit that goes to infinity, it turns into this operator that I spoke of earlier in last lecture that's connected with the second variations of the action. I called it B. Perhaps you remember that the second variation of the action I called T2 could be written this way as delta x sandwiched around an operator B delta x, where the operator B, if we think of delta x as being a function of tau, where tau is an interval from 0 up to t, then B is equal to minus m over 2 d squared d tau squared minus the potential prime, double prime, excuse me, evaluated at x of tau. This is really x bar of tau, it's the classical orbit. So this has to do with fluctuations around the classical orbit and whether they cause the action to increase or decrease. And so this mu which occurs here, mu is equal to the number of negative eigenvalues of the. Perhaps you'll recall that if B has no negative eigenvalues, if all of its eigenvalues are positive, then it means this quadratic expression of its expectation value is positive definite. It means that D is a positive definite operator. And therefore, it means that if you make any perturbation around the classical path, it only increases the action. And if that's the case, then the action is really minimum along the classical orbit, like the books tend to say. But if D has some negative eigenvalues, it's not true. The classical action is not minimum. And the number of negative eigenvalues is this mu here, which appears as a phase in the quantum propagator. So classical mechanics, nobody cares if it's maximum or minimum, because you don't care about the second variations of the action, because all you want in classical mechanics is to get the equations of motion, which are the Lagrange equations, and that comes from just the first variation. But in quantum mechanics, you need the second variation to get the phase right. Now, many people in quantum mechanics blow off phases. They say, oh, I don't care about that. And, well, you know, take that point of view, then you ignore this. It's kind of complicated to do it anyway. All right, anyway, but this is the formula. And this is called the Van Vleck formula. Van Vleck didn't exactly derive it in this form, but this is a more modern point of view of this formula. It's right in the 1920s, actually. All right. Now, what I would like to, so I don't expect you to follow all the details of that derivation, but that's more or less how it works. However, what I will do is show you how to use this formula. And so let me give you probably the first example to look at, which is the case of a free particle. Let's work out the, so this is really our first evaluation, actual evaluation of the path integral, which we're doing in the stationary phase approximations. So we'll take the case of a free particle. Most of this calculation is classical because the S is the action along the classical paths, integral of the Lagrangian along the paths. So let's do that. So the Lagrangian for a free particle is m over 2x dot squared. Now we're thinking about going from an initial position x0 to a final position x, and we're going to do this. The classical path is of course a straight line with constant velocity, and we do this in time t. And so the action, which is s, which is the integral of L dt, or L d tau from 0 to t, is easy to evaluate in this case because the Lagrangian is the same as the kinetic energy, which is constant on the classical path. And so this is just equal to Lagrangian times the elapsed time. That's all there is to it. But that's the same thing as m over 2 x dot squared times the elapsed time. However, Hamilton's principal function is supposed to be expressed as a function of the initial position, the final position, and the time. And here we've got it expressed as a function of the velocity. Well, we get rid of the velocity by saying the velocity is equal to x minus x0 over t. That's really, of course, the average velocity, but for a free particle, it's the same as the velocity, which is constant. So plugging that in, what this turns into is m over 2 times x minus x0 squared over t. Now, by the way, for the free particle, so this x, let me call it u0 of t, x naught. The u0 means the free particle here. We worked this out by using exact quantum mechanics a couple of lectures ago. And the answer is that it's m divided by 2 pi I h bar t, square root of all of that, times e to the I over 2, e to the I over h bar, let me write it this way, m over 2 x minus x0 squared over the time t. And what you see now is that Hamilton's principal function, this is it right here, integral of the Lagrangian over the path is exactly the exponent that came from doing exact quantum mechanics. In fact, this really is the e to the I over h bar s of x, x0, and t, which appears in the Van Vleck formula. It's the same as that one right there. Now, what about the prefactors here? To get them, we merely need to take, we've already found S, we just have to differentiate it twice with respect to x and x0. Tell you what, before we do that, why don't we, as long as we're differentiating S, why don't we verify the Hamilton's generating function relations? Let me do that here, in this space. So for the free particle, as I said, S is m over 2, x minus x0 squared over t. So if we differentiate S with respect to x, you can easily see what you get. You get m times x minus x0 over t. But x minus x0 over t is the velocity, so it's the mass times the velocity, and is therefore equal to the momentum at the final endpoint, which is just what Hamilton says. Let's take ds dx0, differentiate with respect to the initial position. Now there's a minus sign that comes in, minus m, x minus x0 over t, which is equal to minus mv, which is equal to the momentum, minus the momentum at the initial point. And then finally, if I differentiate with respect to time, ds dt, I'll put a minus sign on it here, so it becomes, should be plus the Hamiltonian. You can see what that does. We differentiate 1 over t, so we get m over 2, x minus x0 squared over t squared. This is m over 2v squared, which is the energy of the particle, which is the same as the Hamiltonian. So all of Hamilton's generating function relations are verified. Now, in the Van Vleck formula, however, we need the second derivatives, which is right here. Those things there. We need second derivatives. So let's compute d squared s dx0. So I just take, let's say, this x here, differentiate with respect to x0. We get d squared s dx0. It's easy to do. It just becomes minus m over t. All right? And so, for the case of the free particle, it must be here, because it's not on the other board. For the case of the free particle, this factor here turns into m over t square root. And if we combine it with the square root down here, you see we get exactly this prefactor that came from exact quantum mechanics. And the only thing that's left is this mu thing here, which has to do with the number of negative eigenvalues of the second variation. Well, the answer better be 0. If the answer is 0, it means there are no negative eigenvalues, and it means that on the free particle, the action really is minimum on the classical orbit. But how can we prove that? Let's take this scalar. So in this case, the operator d, since there's no potential, is minus m over 2, d squared d tau squared. And in this case, delta x, d delta x, is then therefore minus m over 2, integral from 0 to t, d tau, of delta x times delta x delta dot. But if we integrate this by parts, this becomes plus m over 2. And remember, delta x vanishes at the end place. D tau of delta x dot squared. And this, as you see, is positive, greater than or equal to 0. And so the result is the operator B is positive definite, and therefore it doesn't have any negative eigenvalues, and mu is 0. Therefore, the action really is minimum along the orbit for a free particle. You can go further. It's not that hard to find the actual eigenfunctions and the actual eigenvalues. But this is an easier argument that shows right away that it's positive definite. So, all right. So that's the derivation for the free particle that shows that it agrees. So let me just make one more comment: is that the answer came out to be exact for the free particle. And the main reason for that is that the Lagrangian for the free particle is a quadratic function of the velocities and doesn't involve the positions at all. The Van Vleck formula is a Gaussian integration, involves second-order fluctuations around the classical orbit, expanding out the second order. But if the Lagrangian is only second order in positions and velocities, this expansion is exact. And so this infinite dimensional Gaussian interval that we just did has to give the right answer. Or generally, it will give the right answer when any Lagrangian has a quadratic function of velocities and positions. This would include harmonic oscillators, free particles, particles with gravitational fields, and it also includes particles in uniform magnetic fields as well. So those are all cases for which the Van Dyke formula would give you the exact answer for the propagator. Right, that's all. Last time I went over the stationary phase approximation, and basically it's an exercise in mathematics. It's an approximation for an integral in which you've got a rapidly oscillating integrand. Here we're thinking of kappa as being small, which is what makes the integrand oscillate rapidly. And I think it went over all right in the one-dimensional case, but for the multi-dimensional case I was pretty sketchy. So I want to start today by filling in more of the details about this multi-dimensional result of the stationary phase approximation. The variable x here is shorthand for x1 to xn, so it's in dimensions, as you can see. And the basic idea of the approximation is that the integral integrand is dominated by the regions of the variable integration x, region of x space, around which the phase phi is stationary. Stationary phase point is defined as simply one where the gradient of phi is equal to 0, and we call that x bar. And so the basic idea is to just expand the exponent around the stationary phase points, carry it out to second order, and then do a Gaussian integral. To do it in somewhat more detail, let me write it like this. So let's take let's take a point x and let's write it as a stationary phase point plus a correction I'll call y, like this. Then we'll expand the phase phi of x and powers of y, which we think of as small. So it becomes phi of x bar, the stationary phase point, plus first correction is the sum on I of y sub I, the derivative of phi with respect to xi, evaluated at x bar. And then the second correction, just doing it. And then lambda, you see, contains the eigenvalues of the original matrix M. Also, let's note something else, which is that the Jacobian, or that the volume element dny is the same thing as dnz, because the orthogonal matrix here, which occurs in the coordinate transformation, has a determinant which is 1. And so the remaining integral here, if I have space to write it down, is first of all this constant factor. It's e to the I phi of x bar over kappa. And then the remaining integral is integral dnz. And then we get e to the I over 2 kappa in the exponent here. And then this quadratic form now turns into this. We can write it this way. It's the sum on j of the eigenvalues, call them lambda j, times z sub j squared. And now the point of this is that this resulting integral in z now factorizes into a bunch of one-dimensional Gaussian integrals, and in effect reduces this to this multi-dimensional case down to the one-dimensional case. Now I'm sort of short on the room here because I got so much on the board. But let's just look at this integral here, and let me do it up here on this board up above. I'll try to cover it all up. So the remaining integral here turns into a product of these one-dimensional integrals. So our I is equal to this prefactor, e to the I phi of x bar over kappa. That's the phase evaluated at the stationary phase point. And then the remaining integral is a product of one-dimensional integrals, so that is the product over j. And these one-dimensional integrals, as I said, I derived the one-dimensional stationary phase across Taylor series. It's a multi-dimensional Taylor series. We have sum on I j of yi times yj times the second derivative of phi xi xj evaluated at x bar. And then there's cubic and so on terms out here, which I don't bother to write down. So this is the expansion of the phase in the neighborhood of the stationary phase point. Now the first order term vanishes because that's the definition of the stationary phase point, is where the gradient of phi is 0. And this is why I went on to the second term, because it's the first non-vanishing term after the value of phi on the stationary phase point itself. So I want to take this phi of x and plug it in here into this exponent. You see the first term is just going to be a constant, and the second term is going to give us a Gaussian integral. If I call this integral I, just to give it a name here, the result is going to be that I is equal to an integral dnx. And then for the phi of x bar, I'm just going to get e to the I phi of x bar over kappa. And then there's a correction from second order. To make this a little easier to write, allow me to take this matrix, the second derivative matrix of the phase, evaluate the stationary phase point, and just define it to be Mij. M just stands for matrix. That's just save writing. And likewise, let me take the entire second order expression here and write it this way as y transpose times m times y, where y is being viewed as an n-dimensional vector, which is being sandwiched around the matrix M. That's just what this whole expression means. So if I do this, and there's another term here in this integral, it's e to the I over 2 kappa, and then we've got y transpose times m times y. And this is now an approximation because we truncated the expansion of the exponent in second order. But you can see that as far as the first factor is concerned, that phi evaluated at the stationary phase point is just a constant. It can be taken out of the integral. And as far as the rest of it is concerned, it's a Gaussian integral. And it's in multi-dimensions now in the matrix M. And it's a purely imaginary exponent, but it's basically a Gaussian integral. The permanent integration dnx is the same thing as dny, because x and y just differ by a shift, just a change of origin is all it is. And so this thing then turns into the central integral is the integral over y times this Gaussian exponent. Now, to proceed with analyzing this, let's let y be equal to r times z, where y is an old vector of coordinates and z is a new one, and r here is an orthogonal matrix. And if we make this substitution in the exponent here, then the exponent, which is y transpose times our matrix m times y, becomes equal to z transpose times r transpose times m times r times z. It becomes a new coordinate z transpose z sandwiched around a new matrix, which is r transpose mr. Now, M is a symmetric matrix. It's a real symmetric matrix because it's just the second derivatives here. So we can choose this R matrix, orthogonal matrix R, to diagonalize this. And let's do that. Let's call this lambda, which is diagonal, as we mentioned last time. Each one of those is going to turn into this. It's going to be e to the I pi over 4 times the sign of the eigenvalue, lambda j. And then what you get is the square root of 2 pi kappa divided by the absolute value of lambda j. That's the result of doing this integral. Now, when we take the product over j over all the variables of the lambda j's down here in the denominator, that's the product of the eigenvalues. That's of course the same as the determinant of the matrix. So the product of the lambda j's is the determinant of this matrix M, which is the same thing as the determinant of the second derivative matrix here. Evaluate the stationary phase point. And that explains this determinant under the square root that you see down here in this answer that I'm quoting. That's where that comes from. As far as the product of the 2 pi kappa, since there's n of these, this goes from 1 up to n, this is going to give you 2 pi kappa to the n. And that explains this factor here under the square root, right there. And as far as the product of the signs of the eigenvalues are either positive or negative. We will assume this matrix is non-singular. And so the product of the signs times the e to the I pi over 4 is just equal to e to the I pi over 4 times the number of positive eigenvalues minus the number of negative eigenvalues. And that's exactly what this factor here is, e to the I nu pi over 4, where nu is defined as nu plus minus nu minus, and nu plus and minus is the number of positive and negative eigenvalues of the second derivative matrix.